You hear it all the time, right? Data is the new oil. It's the fuel that powers all of this amazing AI. But that brings up a really important question. How much fuel does an AI engine actually need to run? Today, we're going to dig into one of the most fundamental questions in all of machine learning. How much data is really enough?
So let's just get right to it. How much data is enough? Are we talking a handful of examples, or do you need billions? Well, the answer, and this might surprise you, isn't just a number. It's actually a concept that's going to change the way you think about AI entirely.
To get a feel for this, just look at this comparison. It's kind of like a tale of two different appetites. On one hand, you have a simple model that might only need a few hundred examples to get the job done. But then you have a massive deep learning model that can chew through millions, even billions of data points. So what's with the huge difference? Well, let's find out.
And let me tell you, figuring this out is not just some academic exercise. This is literally a billion-dollar question. Because knowing how much data you need, that determines everything. Your budget, your project timeline, and whether your massive AI project succeeds or fails.
Okay, so to answer this billion-dollar question, we need the right tool for the job. And in the world of machine learning, that tool has a name: sample complexity. Simply put, it's the formal way of figuring out the absolute minimum number of examples a model needs to learn something well. And not just learn it, but learn it so well that we can be confident it'll work on new problems it's never seen before. This is the key idea we're going to unpack today.
So what does learning well even mean? Well, in machine learning theory, the gold standard is something called probably approximately correct learning. Now, I know, that sounds like a total mouthful, right? But it actually breaks down into two really simple goals. First, you want your model to be approximately correct, which just means it has a super low error rate. And second, you need it to be probably right, which means you have high confidence that it's going to perform that well on new, unseen data. That's it.
All right, now let's build some intuition for how this whole thing works. It's actually a lot more straightforward than you might think.
Let's play a quick game. Imagine I'm thinking of a number between 1 and 10. How many questions would you need to ask to figure it out? Is it more than 5? Is it an even number? You'd get it pretty quick, right? Because there's only a small number of possibilities.
Okay, round 2. Now, what if I told you I was thinking of a number between 1 and 1 million? Whoa. All of a sudden, you're going to need way more hints, a lot more information to have any chance of getting it right. The search just got astronomically harder.
And believe it or not, that little guessing game is exactly what's happening inside a machine learning model. That range of possible numbers, 1 to 10 or 1 to a million, that's what we call the hypothesis space. You can think of it as every possible answer the model could even consider. And here's the kicker. The bigger that space of possibilities, the more data, the more hints the model needs to find the right answer.
So, this space of possibilities is the key. It's what determines a model's hunger for data. Let's see what this looks like with the kinds of models people use every day.
This table just lays it all out, crystal clear. Take a look. On one end of the spectrum, you have something simple like linear regression. It has low complexity. It can really only find simple, straight-line patterns. So naturally, it doesn't need a ton of data. But then, you go to the other extreme, deep neural networks. These things are incredibly powerful. They can model almost anything, which gives them a gigantic hypothesis space. And because of that, they are just incredibly data hungry.
And this leads us to a really important warning. So what happens when you have one of these super powerful models, but you don't give it enough data to learn properly? Well, it's not just that it won't work well. It can actually be dangerous because it leads you straight into a classic trap.
And that trap is called overfitting. This is probably one of the most important concepts in all of machine learning. The student analogy is perfect. Think of a student who just memorizes the answers for a practice test. They haven't learned the material. So yeah, they'll ace that one test, but they'll completely fail the real exam because they can't handle any new questions. That is exactly what an overfit model does. It memorizes, it doesn't learn. So you might be wondering, how do we avoid this trap? Well, thankfully, engineers and data scientists have a whole bag of tricks. They can do things like pick a simpler model if they don't have much data, or they can use clever techniques like regularization and transfer learning to control the model's complexity.
Let's zoom in on one of those tricks, regularization. It's actually a pretty clever idea. Let's go back to our number guessing game. Regularization is like telling the model, hey, listen, I know you can guess any number up to 1,000,000, but for this problem, I want you to stick to numbers between 1 and, say, 1,000. You're basically shrinking its hypothesis space on purpose, which lowers its complexity and, you guessed it, its need for data.
And then there's transfer learning, which is, honestly, a total game changer. Instead of training a model from scratch, from zero, you take a model that's already been trained on a huge amount of data and just fine-tune it for your specific task. It's like giving your model a massive head start. It already has a ton of background knowledge, so it needs way less new data to get up to speed.
So what's the big lesson here? It's that the solution isn't always to just go out and get more data. A lot of the time, it's about working smarter, not harder, by really understanding and managing your model's complexity.
And that really brings us right to the heart of the matter, to the single most important idea we've talked about today. Great machine learning, it isn't just about building the biggest, fanciest model. It is all about the relationship, that delicate balance, between how complex your model is and how much data you actually have to train it.
Okay, so let's bring it all home. With this new understanding, what's the real lesson that sample complexity teaches us about data?
You know, we started with a simple question. How much data is enough? And I think now we can see the answer isn't some magic number. It's a principle. It's about balance. It's all about matching the power of your model to the richness of your data and mastering that balance. That is the true art and science of building AI that doesn't just memorize the past, but can genuinely learn to predict the future.